The point of this video is to show you how one acceleration time graph, this guy here, so one value for acceleration, not changing with time, can give us a whole family of different velocity curves and position curves. And the trick all boils down to these initial conditions. Here I've got the v0 or the x0. So somewhere within some sort of a physics problem, you have to be given your v0 in order to make sense of this. If you have the a, getting the actual curve or the graph that you're going to get of the velocity, well, you can get the slope, but without the v0, you don't have this full equation. So I'm going to give you a couple of examples. So let's start with, what if your v0 equals 0? So that'll be here in my green. v0 equals 0. Well, so that means that when time is 0, I've got no initial velocity. So I'm going to start here at the origin. And then I've laid myself out a couple of dots, and so I can just connect these up, and boom, I get a line for velocity as a function of time. And if I just grab the a and I write that in, so I have here v as a function of time is just 3 meters per second squared times time. So that means every second that time goes on, my velocity increases by 3 meters per second. Okay, well, what if we had different initial conditions? Well, sure. We could have an initial condition that was positive. So let's have a v0 equal to 6 meters per second. So we would just take the same curve and we would shift it up 6 units. And then we would start that, and clearly I'm running out of paper, but that's okay. So we would just have this line. Parallel in slope, I've got my initial v, and so if I just write out the equation, we will get v as a function of time is equal to my initial 6 meters per second plus 3 meters per second squared times time. Now I'm pointing to this because I want to show that that term is the same here. Right? In our line form for velocity, there's our intercept, there's our slope, and there is our independent variable. And these parts don't change in this family. Let me give you another one just for the heck of it. Let's do a v0 equal to -5 meters per second. So I've already got a couple of dots here lined up for me. Connect them up, keep going. All right, so this would be just the same thing. So it would be v as a function of time is -5 meters per second plus 3 meters per second squared times time. Okay, well, can we take these and turn them into position as a function of time curves? Sure, but we have the exact same problem again in that we have to know what our initial position is. So I'm going to take this red and the green and the blue, and I'm going to show you how with our initial position we can get some slightly different curves. What I'm going to do first is I'm going to start with, well, what happens if the initial position is 0? Okay, well, this shouldn't be too hard to figure out. Let's start with the green. So these are all going to give us parabolas because we have an acceleration. So accelerated motion is drawn as a parabola. So I'm going to take my value here, velocity is 0. That's the slope. And so that means here, very near the origin, I should be basically flat. But then we're in a parabola, so the parabola is going to come on and curve up. So don't worry about sketching parabolas perfectly. That's what software is for, but you can get this basic notion that there is this curve that happens. So if we're using my x0 equal to 0, the equation for that would be x as a function of time is equal to 0 plus v0 t, well, that was also 0, plus 1/2 a, which is 3 meters per second squared, times t squared. So this is sort of boring. This would collapse itself down. and we would wind up with just 1/2 3 meters per second squared t squared. Hopefully you can read that all. Okay, well, what about the blue? Absolutely we can do the blue. So here on the blue, the trick, though, is that this means I have a negative slope. Well, a negative slope doesn't mean I move down the x to start, because I'm keeping this same x naught. So I'm going to start here at the origin. To show a negative slope, I have to show downwards angle. Now we can get some other information off of this. So right here at, let's see, 1, 2, 3, 4, 5, 6 ticks over, 3, 4, 5, 6, we have here where velocity is 0. Now really important, that's not where the position is going to intersect with the time curve. That's where velocity is 0, the slope. So I'm going to have a parabola. It's going to start moving down, and somewhere directly below this, the slope is going to be flat. So since I'm just sketching these and I'm not really getting the numbers, it's going to come down like this. Now where will it actually intersect back up here? There's a couple ways you can reason this out. Since this is a simple motion here, we're going to wind up actually with symmetry on either side of this line. Or, really the real answer is if I were to shade in this triangle, and then I were to come on over the same amount of time and shade in the same triangle, which I'm not doing because it'll look awful here, I've tried, then what I would find out is that, let's see, so 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So we should be intersecting here because the area of this triangle and the area of this triangle would be canceling out. So if I try and sketch this, something like that. Okay? And that would be the parabola, the position curve that goes with this velocity curve. So if I were to give this an equation, x as a function of time is equal to x naught is still 0, so I'm not even going to bother writing it. Well, I guess I'll write that. 0 meters plus, but I do have an initial velocity, and it's a -5, plus a -5 meters per second times time. All right, because there's our v naught t, and then plus 1/2 3 meters per second squared t squared. Okay, so that would be the line that describes that. Can I take the red and get a line? Yeah, of course I can. And since I'm stuck once more, we're still using this, so it's going to come out of this origin too. But we're starting with a positive slope. So that means instead of coming out like this, or like negative here that we had, we're going to come on out already angling upwards and then get steeper and steeper as we go. So that would look something like that. Your parabola should never get 100% vertical. So there we go. So this parabola here would go along with this equation, and we could do the same thing out and get the x equation for the red, which I'm going to leave to you guys. What I want to do instead, though, is I want to say, well, what if we take any one of these and we actually give it some sort of an initial position? Well, I'm going to start by taking the red, and I'm going to give it now an initial position up here at 4. So this would be a case where I have x naught equal to 4 meters. Okay? So really all that's going to happen is I would draw in a parallel parabola, and it's just going to look like, let's see if I can do that. Like that. So the line for this sort of pinky purpley magenta here, or I should say the equation, is going to be x as a function of time is equal to my x naught, 4 meters, plus my v naught times t, plus 1/2 my a, 3 meters per second squared times t squared. So this single value for a will give us a whole family of values of lines for velocities, and then these velocities can each give us a whole family. I could have taken this and I could have given it a negative value. I'll do just one last one. If I were to give this a negative x naught equals -6, let's bring it way down here. 1, 2, 3, 4, 5, 6. There. And so it's just going to be the same upward sloping parabola. Something like that. So, one acceleration can give us a whole host of velocities. Each velocity line can give us a whole host of these position lines. And the trick of going up and up and up is you've always got to know these initial conditions. So if you know your initial x, your initial v, and your a, you can always work your way up. But what if it's negative? Well, if it's negative, take everything I've done and just flip it over this way. And I will leave that for another video or for you to try out. Thanks for watching.